Oh, nice. Okay. So this is your cell membrane, all right? And on this, it's made of a couple different parts, all right? Your biggest thing that we have are these right here. One of these individual parts, all right? So one of these things with this is called a phospholipid, all right? So this is a phospholipid. And collectively, this thing is known as a phospholipid bilayer because it's got two layers of those things. Within that, I've got these different areas of charge. Right here, I've got these long lipid tails, and these lipid tails are made of all these hydrocarbons. And so because of that, lipids don't like water. And because they don't like water, it has a term for that. It's called hydrophobic. All right? If it is hydrophobic, it doesn't like water because it doesn't have a charge. If it doesn't have a charge, it is nonpolar. All right? So I've got this area right here. Then I've got this part right here of this phosphate head. This has a charge, and it loves water, so its term is hydrophilic. All right, and it is polar. Down here, same thing, and it is polar. All right, so I've got this hydrophilic area, this hydrophobic area, this hydrophilic area, and so I've got these differences in charge, and collectively, this is known as, when I have areas of different charge, it's known as amphipathic, all right, meaning areas of different charge. All right, because I've got areas right here that are polar and hydrophilic. I've got areas that are nonpolar and hydrophobic, areas that are hydrophilic and polar. So I've got this stuff in there. Then I've got some other parts that are making this up. I've got these green molecules right here. These green molecules are called cholesterol. Guaranteed I'm going to misspell stuff. Whatever. All right, cholesterol. What they're going to help it do is maintain membrane fluidity. When you hear fluidity, what do you think of? Fluid. So like kind of how it's liquidy and it's movable, stuff like that. If it gets too cold, and if I were to take a cell and expose it to something that was very cold, when stuff gets cold, it moves together. And that cell would get very rigid. If those phospholipids got very close together and got very rigid, stuff would not be able to move into the cell. Stuff would not be able to move out of there. The cell would not be malleable whatsoever. And sometimes these cells need to move around and squeeze around and change their shape. This cholesterol right here helps maintain that. When temperature drops, it helps that cell membrane from getting too fluid. When temperature increases too much, it helps from those phospholipids separating out too much. So cholesterol stops that. Then I've got this thing right here. This big thing right here is a type of protein. It's called an integral protein. Or also known as a transmembrane. All right. Remember, trans means across. This is a protein that's going to go across the entire thing. What do you think this is used for? Transport. It's used for transporting things in and out of the cell. Because only certain types of molecules can go in and out of the cell very easily. So there's only a specific type of molecule that can diffuse in and diffuse out of the cell very easily, and that's going to be small and nonpolar. All right, so only small nonpolar molecules can go through easily because if they're small, they can squeeze through here. If they're nonpolar, it gets stopped by this big area right here. And so small nonpolar, otherwise known as hydrophobic. Okay, those are the types of molecules that can diffuse through the cell membrane very easy. Integral proteins, otherwise known as transmembrane proteins, are going to be used to help get stuff through. And then I've got this other one, a different type of protein. If I think of my vision, and I think of like the things that I'm seeing on the side, what kind of vision is that called? So your peripheral vision. This is called a peripheral protein because it's only on one side of the thing. And this is going to be used a lot of times for carrying stuff around. This is a peripheral protein. All right. And so that's all the parts of your, oh, and then this one right here. You have two things that are used for cell-to-cell communication and cell recognition. This is a glycoprotein. So we have glycoproteins and glycolipids. All right, and that's for cell communication. And cell recognition. Cool. Make sense? Okay, so we talked about amphipathic. We talked about the things that can go diffuse through here really easily are small and nonpolar or small hydrophobic molecules. The structure of the phospholipids, all that stuff. Now we got to talk about some types of transport across this thing. Cool. All right. We've got two types of transport. The first one, okay, is passive. All right. So passive transport. What does passive transport not require?
Energy.
No energy. No energy, and so it's going to go from low to high. What the heck did I just write? No, it doesn't. That's stupid. From high to low. Where are we at on that one, Sam? Okay. You needed to, buddy. Okay, it's going from high to low. So, it's like a ball rolling downhill. If I ever mess up, just say, hey, stupid, like, fix that. Okay? So, it's going from high to low. Passive transport. An example of this is going to be, one type of this is diffusion. Alright? And diffusion is going to be the movement of molecules from high concentration to low concentration. Max, do you remember what we said that's an example of this would be? When I've got a very high concentration of molecules right here and it spreads out, what do we compare that to? A fart. Okay? I'm just putting you on the spot because that's what we were just talking about right at the beginning of class. Okay? Sorry. Alright, an example, so this is going from movement of molecules from high to low. Alright? An example is a fart. An aroma thing, a scented thing. Because as that starts to heat up right away, it's going to be the strongest right next to it. It's going to be the weakest very, very far from it. So you might be able to smell that very, very well. Lepe in the back may not be able to smell it that well because it may have not gotten over there. Yesterday with that thing that burnt in here, up here, yeah, it smelled a little bad, but if you went back to like where the ladies are in the back row, it smelled terrible because it's right next to the microwave where it happened. So that's diffusion. All right, an example of that's going to be a fart. So that's going to be like, at the beginning, it's all right here in the beginning, or right here. As time goes on, it's going to spread out everywhere. Okay. So that's type 1. The other one is going to be osmosis. Osmosis is the movement of what? Yeah. The movement of free water. So from free water from high to low. Okay? From free water to high to low. And so I've got a couple terms with this. Term number 1 is going to be hypertonic. If it's hypertonic, does it have more or less solute? More. Okay? So it's got more solute. What about free waters that have more or less free water? It's got less free water. So more solute, less free water. Okay? More solute, less free water. Hypotonic is going to have less solute, more free water. Okay? and then iso, same. Okay, so an example of this would be our first one. Let's say I've got this cell. Within this cell, it is 0.2 molar. On the outside, it is 0.1 molar. All right? So on the inside, does that have more stuff or does that have less stuff? If it's 0.2 molar, it has more stuff. So would this be hypertonic or hypotonic? This is hyper. This one right here is hypo. And do you remember what we said is always, always, always our rule on osmosis? Water always moves from what to what? Water always moves from hypo to hyper. In osmosis, if it's just occurring naturally, water is always going to move from hypo to hyper. So we said this is a hypotonic, this is a hypertonic. Water is going to move into the cell. It's going to cause the cell to swell up. If I've got something else right here, okay, and in here it's 0.5 molar, and out here it is 0.7 molar. Okay, is this hypo or hyper on the inside? This is hypo. Out here is hyper. Water always moves from hypo to hyper, the cell is going to shrivel. Okay? So if I said I took a piece of celery or a carrot and I stuck that carrot into a solution, and after 2 hours I noticed that the weight of the carrot had increased. Okay? So if I took a carrot, let's say, here's my carrot right here. That's my carrot. In the beginning it was 100, let's say it's 100 grams, tiny carrot, okay, baby carrot. And then I stuck it into a solution. After, let's say, 30 minutes, now my carrot, oh, that's carrot 2. Now my carrot's got a weight of 250 grams, okay? It was in this solution, and now the carrot gained weight. So did water move into the carrot or out of the carrot? Water moved into the carrot. Therefore, what can be concluded? Was the carrot hypotonic, isotonic, hypertonic to the solution?
Hyper.
The carrot had to have been hypertonic because water always moves from hypo to hyper. Water moved into this carrot, thus why the carrot gained weight. Therefore, the carrot had to have been hypertonic because it gained weight. Make sense? Any questions on osmosis? Okay. How about you? I don't know if you, yes ma'am? Do what? You got scared? You can take a picture if you want before I erase anything. Scalise's filming all this. I'll put it on Classroom. Don't film me. Film the info. I'm useless.
You misspelled movement.
You're on trend. Hey, you got a big shout out on the email today from Cerny. Like every teacher, like, Monica's great. She's a scholar athlete. She carried the team yesterday. Stubbs responded like it's all over. Whole school saw it. The email is even titled Monica Ramirez. No, it was about how you carried the team, how you've been a great asset to the team your entire time you've been on it. Like, I'll tell you. I knew you'd be embarrassed. Right when I saw it, I was like, oh, she's gonna.
Yeah. Buy a snack.
There's a small party that's like, oh my god, that's embarrassing. Alright. And then finally, another type of passive transport that I have is called facilitated diffusion. Facilitated diffusion. Alright, so facilitated diffusion is still passive, it's still high to low, alright, but it needs help. Do you remember which kind of molecule it uses to help it? It needs help from proteins.
Yes.
No, I never recorded it. Alright, and so there's two types. I can have channel. All right. So these channel proteins are less specific. All right, or I can have carriers. All right, and these things are specific. These would be good for helping move in large or polar molecules. Okay. Then I get to my next one. Okay, if it's active transport, what does it use? Uses energy. All right. An example of this is going to be exocytosis. Okay. So if I've got something that I need to get out, let's say I made like glycolipids or glycoproteins that I need on the outside of the cell, because we said those glycolipids and glycoproteins are used for cell communication and recognition. So I want them on the outside. So what would happen there is I put these things that I just made, these proteins, and if they're a protein that's meant for the outside, was it made on a free-floating ribosome or a ribosome that's bound to the inside of the reticulum? If it's made for the outside of the cell, it's made on a bound ribosome. All right. So I've made all these things on the outside of it that I want on the outside of the cell. All right. And so they're in a bound one. All right. And it's going to head towards that cell membrane. And so what's going to happen is it's going to get there. It's going to bind with that cell membrane. So I've got all my stuff that I made on the inside of this. All right. It's going to bind with that, and eventually it's going to get absorbed by the cell membrane. And so if I want something to be on the outside of the cell membrane, remember, I need it to be on the inside of that vesicle. All right. If I want it to be on the inside of the cell membrane, I need it to be on the outside of the vesicle. That's the question that we had of if I was making something that I wanted for the outside, and I asked you, and I had it like I was in here, like this marker, and I said, if I want it to be on the outside of that wall, did it need to be on the inside of the outside? We said, if we want it on the outside, it needs to be on the inside of the vesicle, because I'd go up to the cell wall, and then, all right, and it's on the outside. Whereas if it were like this, it'd go, and now it's on the inside. Okay? Any questions? None at all? All right. I want to make sure those potatoes aren't burning. Nothing's burning over there, is it, Sabrina? Yeah. You're on potato duty, just make sure nothing smokes. I don't need to evacuate the classroom twice. All right. Then I've got, so that was going to be that one. You already got that on there. And so now I get to, where are we at? Endocytosis. All right, endocytosis is active transport. If I've got endocytosis, which way do you think I'm moving stuff? Into or out of the cell?
Into.
Into the cell, thus the endo. All right, it's telling you that. And there's a couple types. I can have phagocytosis. All right, what's going on there? What's it doing? It's cell what? Cell eating. All right. So it's not specific. I can also have penocytosis. Someone said it reminds them of they call it different. Instead of saying a pina colada, they say a pino colada. All right, and so they think of a drink. Because penocytosis is cell drinking. All right? And so, not specific. This is for moving in bulk goods, solid stuff. This is for moving in bulk liquid goods. And then I've got one other type of endocytosis. That other type was called receptor mediated. All right? And so the thing about this one, can I say something real quick? Yeah. The thing about this one, it's going to move molecules in, but this one is very specific. Okay. Receptor-mediated endocytosis is very, very, very specific. Okay. The last type that we talk about is something called Co-transport. What are you giggling about, Talise?
Nothing.
So this is active, all right? And let's say I've got this cell membrane. Okay. I've got okay, let's say I want to move this molecule in, and this molecule is, let's say it's right here, it's sucrose. Okay? But sucrose cannot come in on its own. And so what I've got to do is I've got to get sucrose an escort to come in. All right? That's why it's called co-transport. It happens together. And so in order to do this, all right, what I'm going to do is I'm going to pump something. It can be any different number of things. It could be hydrogen, it could be sodium, it could be potassium, it could be any number of things. But for the sake of this one, I'm going to pump hydrogen. If I want to pump it, all right, so this is going to be called a proton pump. If I want to run a pump, what do I need to have in order for a pump to work? I need energy, all right? And so I'm going to have energy, and that energy is in the form of ATC. ATP is going to come in. It's going to pump a hydrogen across, all right? And so what's going to happen is it's going to start creating this big old concentration gradient of all these hydrogens, all right? And so it creates this electrochemical gradient, meaning I've got this difference in charge because I've got all these hydrogens over here. Do you think it likes that? It doesn't. It doesn't like these things. And so naturally, this is going to want to go from high concentration to where there's a lower concentration over here. So it's going to go through this molecule right here, all right, this co-transport protein. When it does that, all right, this hydrogen is going to go through. When it does that, it's going to suck a sucrose molecule through with it. So that's why it's a co-transport molecule. This is going to transport across, but it can't do it by itself. It's got to do it with the help of something else, an escort. All right, and so we got those escorts there by pumping them across, and now I can have sucrose inside of my cell. What might be one of the best ways to inhibit this sucrose from coming in? So let's say we've got something that inhibits that sucrose. What would be the easiest way, you think, to stop sucrose from coming into the cell? No, ignore enzymes. Haven't even touched enzymes yet. I don't want sucrose into the cell. What can I do to stop sucrose from coming into the cell? Stop this. If I inhibit this, if I stop this thing somehow, now sucrose doesn't have its escort. All right? It'd be like, let's say you want to go to a dance or something, but you have to go with a date. All right? And so we've got all these dates. If I want to stop people from going to the dance, I just stop the dates, the availability of those dates. These are their dates. These are the people wanting to go to the dance. If I stop the availability of the dates, now nobody can go to the dance. Okay? That's co-transport. I'll tell you right now, that question's on your test. That's why I went into that. Because that's a hard question a lot of people miss. All right, this is it for membranes. Now we're about to do enzymes. So, do you need that? Yes. Elisa's live streaming it to Instagram and Twitter and I don't know what can you live stream on? I think it came on Facebook.
YouTube.
Periscope. Twitch. That's what someone said last period. Twitch, yes.
What?
Okay. Let's talk about enzymes.
You're gonna get like the people watching that video dizzy. And then with all the
How you guys doing? What time are we out of here?
15.
Oh, time flies when you're having fun. Ooh, I'm gonna slip. No, because then you have to have a sub, and then your test gets put back in further. Okay. Chapter 6.
Chapter 6.
Okay. So all of this, I'm going over this right now. Like I said, I'll be here every day at 6:30 in the morning. So if you ever want help on any more of this, feel free to come in. There's also the online textbook and stuff that has practice quizzes. There's the videos that you could watch to help you go over any of this. If you're watching the Bozeman videos and stuff like that, pay attention to them. Don't just let it play in the background and then text message while doing it. Actually sit and take in what he's talking about. Yes.
When's the test?
Wednesday.
Okay.
Yep. You're doing a lab Monday, Tuesday, test is Wednesday. Because the classroom almost burned down yesterday.
Good thing I wasn't here.
Yeah. Okay. Metabolism. Metabolism. There's two parts to metabolism. It's not only the breakdown, but what else is it?
Build
The
up.
build up. But I've got big fancy names for those words. Alright? Yeah. I've got big fancy names. What's the big fancy name to build up molecules? Anabolism or anabolic. Okay? Anabolism. Let's put that. In an anabolic reaction, I'm going to build up molecules. If I'm building a molecule, does it require energy or do I get energy off? If I'm building something, it requires energy. Alright, so this is going to require energy. If it requires energy, do you remember what we called it? A chemical reaction that requires energy is called endergonic. Alright? Because energy must be consumed, that's why it's requiring it. It's endergonic, and what kind of a delta G does it have? It's got a positive delta G. Okay? So it's got a positive delta G. Okay? And we said the amount of disorder in a system or the chaos in a system is called entropy. If I'm building something and I'm putting energy into the system, I'm creating more order. All right? I'm getting rid of disorganization. And so what I would actually do is anabolism decreases entropy. Okay? And so now I've got the opposite one. What's the opposite of anabolism? Catabolism. How's life out there? Alright, catabolism, what is that doing to molecules?
Breaking down.
Breaking them down. Breaks down. If I'm breaking down a molecule, is it releasing energy or is it consuming energy? Releases. Alright, it's going to release energy, therefore it is what gonic? It is exergonic. It's exergonic, and therefore if it releases it, it gives energy off. That means I have less energy than when I started with, so I am what, delta G? Negative. Okay? Negative delta G. And so now I'm giving off all this energy, and remember, energy transfer is not 100% efficient. Some of it's going to get lost in the system or in the universe, and a lot of it oftentimes is heat, which is the most disorganized thing. And we had a term for disorganization was entropy. So as I'm doing this, I'm going to increase entropy. So catabolism increases entropy. Okay? Makes sense? Cool beans. All right. Now let's talk about types of energy. An extra belt. I have this one you could use, like for the rally. Yeah, you can use this one. Yeah, you can use that. Just come find me later, because right now it'll fall down as a dead. Oh no, you can use it for the rally. I can just hold my pants in the rally. I'm not. Okay, so kinetic versus potential. Potential. All right. Potential energy is energy due to what?
Location.
Energy due to position or location. Due to position. Can you remember some examples of that?
What about a dam?
Okay, water behind a dam. A hamburger. Glucose. Gasoline. Okay? If you think about all of these, not moving, not moving, not moving, not moving, none of these are actually moving. They're just kind of sitting there. But there is potentially a lot of energy if we do something with it. And then I've got the other type of energy, that's energy due to movement. Remember what that's called? Kinetic. Okay? Energy due to movement. And so some examples of that are going to be mechanical. Light. Heat. Waterfall. When I looked at the results from your quiz last Friday, this is yours. One of the questions was, which of these is potential energy? And the answer was glucose, because there's a lot of energy there if we break those bonds. A lot of people put a waterfall. All right, water falling down a waterfall is potential energy. Water behind a dam is potential energy. Water falling over a waterfall is kinetic energy. What's the difference between the two?
Water's moving.
Water's moving, water's sitting still. Okay? There's potential there because it's sitting there at a high gravity. It's got all this gravity pulling on it, but it's not actually moving yet. This one, it's actually moving. That's why that's kinetic energy. Okay? All right. And then I go to this one. All right. So in an ATP molecule, I've got some parts. I've got an adenine. I've got a ribose sugar. And I've got 3 phosphates. Okay, we've got an adenine, a ribose sugar, and 3 phosphates. Do you remember what molecule we said this is the same thing as?
Nucleotide.
A nucleotide. It's made of the adenine nucleotide. Is it the adenine of DNA or RNA, though?
Both.
Can't be both. Why? If it were DNA, what kind of sugar would that be? It would still be that is a pentose sugar. That's a 5-carbon sugar. It would be very, 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 very similar. Something would be different though. It would be deoxyribose. This is a ribose sugar. So yes, it says RNA, all right, but it's a ribose sugar. That's how you know. Deoxyribose would have DNA would have a deoxyribose sugar. This just has a ribose sugar. That means on DNA, so it means right here, ribose has this. On DNA, it just has that. Okay, it's missing that oxygen right there. All right, so I've got this thing right here. How do I get energy from it? I break off this 3rd phosphate. And so what happens is water comes in and breaks that thing off, and it's going to give off energy. Okay? It's going to go in there and it's going to break that off. Do you remember what this process was called of using water to break things?
Hydrolysis.
Hydrolysis. All right, so let's say I've got this ATP molecule, ATP, and it's going to give off one of its phosphates. So I'm going to put inorganic phosphate. You'll always see a phosphate by itself labeled as P with a lowercase I. It's inorganic, meaning it's not attached to this thing that has carbon on it. So that's an inorganic phosphate, and that's going to get picked up by, let's say, molecule B. Okay? The process of ATP giving a phosphate to molecule B. What was that process? Do you remember what that's called? When ATP gives a phosphate to another molecule to energize it, it's called
Phosphorylation.
Phosphorylation. And so this process is called phosphorylation, and we can say molecule B was what? Phosphorylated. All right. So molecule B was phosphorylated. Cool beans. All right, take your picture before I erase this and start drawing energy diagram. Okay? Yeah.
I hope I can hear you.
Me too.
Most likely.
I hope it's not the whole time of Mariah just sitting there whispering, buy snacks for me.
No, you'll hear a little bit of for the video.
Good morning, Coach Johnson. Oh, it smells better. Your son came to me that I have a huge favor to ask. And I go, what? He goes, can you please buy me sugar cereal? I haven't had sugar cereal in 5 years. My parents don't allow it now. He goes, I saw Waffle Crisp and I've always wanted to try it. And I told Lorena and she goes, oh, it's true. I was eating a cupcake one day at school and the kids all came up to me and go, ooh, don't let Miss Johnson see that. She'll snatch that right out of your hand. That's what he said. He goes, they love me too much. They need to just let me get fat. So, yeah, we are. I bought him a box of cereal, but we wrapped it in 2 rolls of Stay Back. Alright, energy diagrams. Not fork away.
No, you can't.
Guys, what if you just got caught in trouble
For what?
for eating sugar
No.
cereal?
The other day he came in here with like 10 Jack in the Box tacos. No, it's just like Brett and Robin won't buy sugary cereal for themselves. Like they do the grocery shopping, they won't buy sugary cereal. They don't care if he has it, but they won't buy it for him. He goes, all we have is like grape nuts and Raisin Bran.
I love Raisin Bran. Yep. Raisin Bran is so good.
Because I don't even remember what sugar tastes like. Okay, energy and time. Okay. This is an energy diagram. And on this thing, we've got a couple different levels. What time are we on here? Oh, okay. We've got a couple different levels. And so what I've got here is I've got this one right here is going to be E of A, or E of A stands for activation energy. E of A without an enzyme. Okay? This one right here, from here to here, is E of A with, okay, E of A with enzyme. Okay, and then from here to here, you know what that would be? Delta G. Specifically for this one, it's negative. So you might see a question that says on here, let's say this is line A, this is line B, this is line C. It'd say like, which line identifies the amount of energy required without an enzyme? That'd be this one. Activation energy is the energy needed to start a chemical reaction. All right. Enzymes lower that. Enzymes do not provide the energy. It's a very, very common misconception. A lot of people put that when they're answering test questions and quiz questions and stuff. Enzymes don't actually give it the energy. It lowers the amount that's required. All right? So activation energy without an enzyme takes longer. Enzymes speed up chemical reactions because they lower that amount that's needed. If I were to ask you on here, what does not change whether or not an enzyme is present, or whether an enzyme is present or not? What does not change? So which of these lines would not change? Delta G. Delta G is right here, so right here. It does not care what's right in the middle, those intermediate products. Okay, so we're going to stop there. All we've got to talk about now is parts of an enzyme and regulation. Day 1 of the lab goes pretty quickly, and so we can talk about this at the end.